So in the last lecture, we discussed about system of single particle, the motion of of single particle. So there we discussed about the force, the moment, the linear momentum, the conservation of linear momentum, and then the torque and the corresponding angular momentum, then the conservation of angular momentum, and the conservation of total mechanical energy. So these were all for single particles. So now we are moving towards a slightly complicated, it's a system of particles. No, it's a many particle system. So for many particle system, you can have in, let's say we have n number of particles. So then this is the coordinate system. So X, Y, Z, and let's draw that. Let's say we have, these are the particles. So we can have many of such particles. So the position of each particle, let's say this is the ith particle. So the position of this ith particle is defined by Ri, and its mass is denoted by MI. Okay, so MI is the mass of the ith particle, and it's the position of the ith particle is the Ri vector. Then the force that acts on the ith particle, you can write if I, there is a net force acting on the ith particle, that will be the external force acting on the ith particle. So if we apply an external force on the ith particle plus, so now if we have many particles, then this one particle, I mean, every particle can exert force on each other. So this ith particle, on this ith particle, all the other objects, all the other masses will I mean, they can exert force. So that we can write like sum over of all j, where j not is equal to I, because if j is equal to I, then it will be for same particle. A same particle, it cannot exert force on itself. So that's why j not is equal to I, and then sum over all the forces due to all other particles. This if ij, this means force on ith particle, by jth particle. So this is the external force on ith particle. So and these two, summation of these two will be the total force on ith particle. So summation of these two is the total force on the ith particle. Now, for each particle, then the second, for each particle, or let's say for ith particle, second law of motion, I mean Newton's second law of motion. Newton's second law of motion is the acceleration, that is mi, I mean the mass times acceleration. So mi is the mass times acceleration, that means d2 ri dt2. Acceleration is a vector which is a uh, 2 times derivative, double derivative of the position, that is equal to the total force on ith particle. That means external force on ith particle plus sum over all j, where j naught is equal to I f of ij. Okay, so this is the equation of motion for a single particle, for a single ith particle in the system of n number of particles, let's say, in a many particle system. So then if we sum over this equation, this, let's call this equation 1, and if we sum over for all the particles in equation 1, then sum over all I is mi d2 ri dt2 is equal to sum over all I if I ext plus sum over all I sum over j not is equal to I f of ij. Okay, so this we can write, we can take the derivative if the mass of all individual particles are constant, we can take this derivative out. So we can write d2 dt2 of sum over I in I ri equal to sum over I if I external plus sum over I j, where I not is equal to j f of ij. Okay, let's call this equation 2. Now what is this sum over I if external I? This is the net external force, because if we sum the external force acting on each particle, we will get the net external force. So we can write it like the net external force f ext. And what about this second term? For the second term, we will apply the third law of Newton. So according to third law of third law of I mean according to Newton's third law of motion, third law of motion, f of ij, which is minus of fj, that means force acting on the ith particle by jth particle is equal, but in the opposite direction of the force acting on the jth particle by I particle. This is a Newton's third law of motion. That is, action and reaction are of equal magnitude, but they are in opposite direction. So in that case, for f of ij plus f of ji is equal to 0. So let's call it equation 3. This equation 3, that is also known as this equation 3, which is basically the third law of Newton's third law of motion. This is also known as the weak law of action and reaction. Okay. So why weak law? Because I mean there must be a strong law then. So we will come to that strong law of action and reaction. So for it is called weak law because it just applies the third law of Newton. Newton's third law of motion. It doesn't take anything more. So for strong law, you will see that there will be another condition on that. So it will restrict the condition more for strong. So this is called the weak law of action and reaction. So if we apply this, so then let's look at the second term again. So there will be sum over all ij. So if there is terms like 1, 2, there will be terms like 2, 1 added to that. There will be ijth term and there will be jith term added to that. That means all the summation, this will be 0, because for each fij there will be a fji, because I and j will run from 1 to, let's say if you have n number particle, both will run from 1 to n. So for each ij we can have fji added to that. So this means we can always have these kind of combinations, and we can make this summation 0. Okay. Then the equation 2 will be d2 dt2 of sum over I minus Ri is equal to the net, total external force. Okay. So let's call it equation 4. Now let's define a new quantity. This is center of mass, COM. Center of mass, this is basically a position. So defined by capital R, denoted by capital R, which is typically sum over all mi Ri by sum over all m. So this R is called the center of mass. Why it is important? We will see later. So for the time being, let's just focus on the definition. So then we can write this I mi Ri, and sum over all mi we will write is at capital M. That means, so This is the total mass. M is total mass of all the particles present in the system. Okay. Then we can write sum over I mi Ri, which is basically equal to A mass. Total mass times the center of mass. Then the double derivative of mi Ri is equal to the double derivative of mi. Now again we will consider that the total mass is not changing. So it's not changing with time. The total mass is not changing with time. We will assume that it's kind of the inherent property of the system, I mean of particles. Then d2r dt2. So this is basically the acceleration of center of mass. Okay, so we will write it as m. So we will write it like d2 dt2. So where all I mi ri basically will be equal to m d2r dt2. Or maybe you can write it like a c o m, acceleration of center of mass. Okay. So from equation 5 and this equation 4, this is equation 4. Okay. So from equation 4 and equation 5, from equation 4 and 5, you can write m a c o m is equal to f x t. So this is kind of, I mean, it's kind of a generalization of Newton's third law for a many particle system. So it is similar like F equal to ma, but here the m is the total mass of the system of particles. A is the acceleration of center of mass, and F is the external force, total external force. So here you can see the importance of the center of mass. So what the center of mass is doing, it's like you can treat the entire system, the whole mass that is distributed over position, you can treat it like a single object of mass capital M, and then you can assign its position at its center of mass. And if then you don't need to consider all the forces, all the forces of particles that the one particle exerts on each other. So you only need to account the external force, and you can study the motion of the center of mass. basically. So you can treat the entire system as a single point, as a single particle of mass m concentrated at center of mass, and you can study its equation of motion. Okay, so this is the equation of motion of center of mass for many particle system, for many particle system. So now, so let's call it equation 6. So now I forgot to define one thing, that is the momentum. We will denote it by capital P, the momentum of the system of, which is basically sum over all, sum over momentum of all the individual particles. You know? So sum over all Pi, which is equal to sum over all Mi Pi. Pi is a vector, and this Vi is Mi ddt of R. This means P, okay, I am denoting it by capital P. This total linear momentum P, this is equal to ddt of sum over Mi Ri, which is basically ddt of R from the definition of center of mass. Okay, so this is basically equation. This is basically this equation. Okay, sum over all Mi are equal to Mr. Capital R. Capital R is the center of mass. So the momentum of the system of particle is which is same as like m dr. So here we can also see that like by considering the whole mass concentrated at the center of mass, and then the momentum will be same like the single particle. So the center of mass basically gives the position where we can consider like the whole system is concentrated at that point, and we can study its motion. So then dp dt is equal to d2 dt2 of MR. And what is d2 dt2 of MR? From equation from equation 5, that is m times, so this is the d2 dt2 of dt2 of MR. So this is m times the acceleration of center of mass, and which is basically, according to equation 6, it's the net external force. Then we can write like This is m into d2r t2, total mass times the acceleration of center of mass, which is basically f ext, the total external force. So the equation we got here is this gives the this equation tells like the rate of change of total linear momentum of the many particle system is equal to the net external force acting on the many particle system. Okay, so then we can have a conservation principle here also, like in the single particle system we we had the equation dp dt is equal to f, where p is the momentum of the single particle, and from there we uh, got the conservation principle of linear momentum. So for here also, for many particle system, we can have the conservation principle of linear momentum. If ext, the external total external force, is equal to 0, then p is equal to constant throughout the motion. This also means like the momentum of COM, momentum of center of mass, is constant. So this is called the conservation of linear momentum for many particle system. This equation tells like if we have no external force, the momentum of the center of mass, momentum of the entire system. So P is basically the momentum of the entire system, you know, momentum of the entire system, sum over all EI. That will be constant, that will be conserved. So it's not saying that the momentum of all individual particle will be conserved. That can change. So for each individual particle, they can collide with each other and they can change their momentum, but the momentum of the entire system, that will be conserved. So this is the conservation principle of linear momentum for many particle system. And the weak law of action and reaction, that plays important part here. Okay.